In this lesson, we're going to look at 5.11. We're going to be looking at catalysts. So the learning objective states that we should be able to explain the relationship between the effect of a catalyst on a reaction and the changes in the reaction mechanism. So we had briefly talked about catalysts in 5.1, and we had talked about that a catalyst was a material that was used to speed up a reaction. So that was able to, adding a catalyst would increase the rate of the reaction. And we did talk about in previous objectives that catalysts were not consumed in the reaction. If it was consumed, it would be found in the middle of the reaction, but our catalyst will be found as a reactant and then found as a product. So it really wasn't consumed, it was there the entire time. So in order for a catalyst to increase the rate of the reaction, the addition of the catalyst must increase the number of effective collisions or provide a reaction path with a lower activation energy relative to the original reaction coordinate. So in a reaction mechanism containing a catalyst, the net concentration of the catalyst is constant. That's why we cross it off just like the intermediate. Now let's talk about the first one. A catalyst must increase the number of effective collisions. Okay, so if we look at this example right here, based off these two graphs. Let's look at the bottom right first. If we were to add a catalyst to increase the number of effective collisions, what we would do is, if you look at this activation energy, if we're going to decrease the activation energy, we're going to show the catalyst more moved over to the left. So here, this would be an example of the catalyzed version of the reaction. Okay, so here, assuming that kinetic energy, this was 0, here we would decrease activation energy, and you can actually see, based off previously, you can tell that we now will have more collisions happening, more effective collisions with that lower activation energy. You'll have more particles colliding, even compared to the low temperature, which was more evident. Here, you can see that there is a lot more, especially for the low temperature, which probably needed it more. Then for the next part, let's look at providing a reaction path with a lower activation energy relative to the original coordinate plane. So if you look at the graph on the left, if we added a catalyst, okay, oh sorry, I know I was blocking the information. If this is our reactants and products, okay, if we add the catalyst, and this is our first activation energy, A is our activation energy. Now, don't get startled with B. B is our delta H of reaction, which does not affect anything to do with this reaction if we add a catalyst. If we add a catalyst, hold on one second. Here, it's going to lower the activation energy. So here would be an effective way of showing a catalyst was used. Here, it did not, if you notice, it did not affect the reactants and products energy, which did not affect delta H reaction. All it did was drop the activation energy lower for that required energy to get over the reaction, okay? So here, it affected activation energy needed, not delta H reaction, okay? All right, moving on. There are a few things I want to mention about the different types of catalysts. First thing is, some catalysts accelerate a reaction by binding to the reactant itself. The reactants are either sometimes oriented more favorably, so sometimes that catalyst will bind to the reactant and will move it and find the correct orientation spot, or it can also react with a lower activation energy. There is often a new reaction intermediate if you use a catalyst, but again, we won't see that intermediate because it will go away because it's consumed. But many enzymes actually function in this manner. Some catalysts involve covalent bonding between the catalyst and the reactants, okay? There also are surface catalysts, which can be a reactant or intermediate binds to or forms covalent bonds with the surface. This actually will introduce elementary reactions involving these new bound reaction intermediates. I would not stress about definitional don't have any definition concerns when trying to explain a surface catalyst. It's trying to say that there's just different catalysts out there. All right, so I have an example for you, just trying to put everything together, and I know you have everything in place to figure it out. So why don't you pause the video, give this example a shot, and then when you're ready, click play, and I'll go over the answer. So based off this example 1, the overall balanced reaction after crossing off the species that were the same on either side, I crossed out the C's and the D's, I got A plus 2B making 2E. So a student suggests that A was a catalyst for this reaction, but they are wrong. So explain why and identify the catalyst. So A cannot be the catalyst because nowhere else in the reaction did A pop up again. Okay, if A was a catalyst, it need to have been found in like the very, very last reactions products. So A could not have been our catalyst. Now D actually will be our catalyst. Now, just because it didn't show up at first in the first step, it did show up first in step 2 as a reactant, but then later it was still the final product in the end. So that still would correlate as a catalyst. The intermediate in this example would be the C. Okay, so C showed up first as a product and then showed up later in a reactant. That shows that it was being consumed. So this would have been an intermediate. Lastly, propose a rate law that is consistent with the reaction mechanism. Looking at my slow step, my rate law would be rate equals K, A to the power of the first order, and B to the first order as well.